Nanotechnology is one of the things that got me interested in science as a young kid. But what is nanotechnology? Most people vaguely know that it involves science and engineering at extremely small length scales. Science fiction fans might imagine a legion of miniature robots working in unison to do cool things. In the Marvel Cinematic Universe, Iron Man's suit is constructed by a swarm of tiny robots that form-fits around Tony Stark's body. On the other hand, futurists might imagine the legion of tiny robots inside the body instead of outside, fighting diseases and repairing cells to keep us healthy in ways our biology cannot. But what is nanotechnology to actual scientists and engineers working in the field? How are they using nanotechnology to improve our world today? And what about the tiny robots in science fiction? Is that just a pipe dream or a vision of things to come? Greetings, Earthlings. Welcome to Science Fictionally True. On this channel, we talk about the real science, technology, and history behind science fiction topics. In this episode, we'll deep dive into what nanotechnology really is, according to scientists and engineers working in the field. Nanotechnology can be a very vague term, so we'll first try to define it. Second, we'll explore how nanotechnology developed into a science and where the field is today. Lastly, we'll go over the science of why working at the nanoscale allows us to do cool things we wouldn't have been able to do at normal length scales. So let's first define nanotechnology. This is surprisingly hard to do. Even to practitioners in the field, nanotechnology is a nebulous term and there still isn't a standard agreed upon definition. Unlike mature sciences such as physics or biology that's been around for thousands of years, nanotechnology only started being recognized as a science by the scientific community about 60 years ago. And today, in many ways, the field is still trying to figure itself out. However, most practitioners may agree on the following general definition. Nanotechnology comprises of structures, devices, and systems having novel properties and functions due to their arrangement of atoms on the 1 to 100 nanometer length scale. Most people understand that a nanometer is very small, but it's hard for us humans to really wrap our heads around nano-length scales because all the things we're used to dealing with are so much bigger. A nanometer is 10 to the negative 9 meters, which is 1/1,000,000th of a meter. For comparison, a modest-sized home in the United States is maybe about 10 meters wide. A strand of human hair is about 100 micrometers wide. That means the width of human hair is 100,000 times smaller than the width of a house. And 1 nanometer is about 100,000 times smaller than the width of human hair. Hopefully, this gives you an idea of how small things at the nanoscale truly are. Despite nanotechnology being a nascent branch of science, humans have been playing with nanoscale matter for a long time. In the 10th century, Europeans colored church windows by embedding gold nanoparticles in their glass. Different sized gold nanoparticles resulted in different colored glass, a consequence of nanoscale effects, although the 10th century Europeans didn't know it at the time. The first pivotal moment in the field's history as a science occurred in 1931. German scientists Ernst Ruska and Max Knoll built the world's first transmission electron microscope. In their first prototype, they were able to achieve a magnification of 15 times. That magnification was nothing spectacular, but it did show proof of concept, and there was plenty of room for improvement. The best transmission electron microscopes today can magnify objects more than 50 million times. For the first time in history, researchers now could see the structure of nanoscale objects. And in 1986, Ruska and Knoll shared the Nobel Prize in Physics for their pioneering work in electron microscopy. We'll go over how a transmission electron microscope works, as well as other tools commonly used in nanotechnology labs in a future episode, so please tune into it when it's available. Scientific research was already being done at the nanoscale in the early 20th century, but scientists still didn't recognize nanotechnology as a distinct field yet. All that began to change after 1959, when American theoretical physicist Richard Feynman gave a seminal talk at Caltech titled there's plenty of room at the bottom. Feynman speculated on all the things that would be possible if we could arrange the atoms in matter, one by one, precisely the way we wanted. If this was possible, the technological applications were endless, and people began taking note. Feynman's seminal talk was the world's first introduction to the concept of nanotechnology. In 1986, American engineer and nanotechnology pioneer Eric Drexler expanded on Feynman's visions when he released his book, Engines of Creation. In this book, Drexler described ways we could manipulate atoms and synthesize new materials. He also introduced the concept of a molecular assembler, which has become a staple in science fiction. A molecular assembler is a proposed machine that can guide chemical reactions by positioning reactive atoms and molecules with atomic precision. A working molecular assembler allows you to create literally anything from the bottom up if you have the constituent atoms. The most famous example of a molecular assembler in science fiction is the replicator from Star Trek. Drexler also introduced the concept of the nanobot, which are robots or machines whose components are at or near the nanometer scale. As we progress towards the end of the 20th century, nanoscale scientific research proliferated and the applications of nanotechnology became more evident. So much so that in the year 2000, US President Bill Clinton made nanotechnology research a national priority by introducing the National Nanotechnology Initiative. This initiative is the first coordinated approach to move the field forward on a grand scale. It came with $495 million in funding in 2001. Furthermore, it also motivated funding from other universities, businesses, and even governments. The initiative's mission statement is to develop new products and techniques based on nanotechnology, to build an educated workforce to support nanotechnology, and to study the effect of nanotechnology on the environment and society. And funding has been ongoing. In 2021, the federal budget provided more than $1.7 billion to the National Nanotechnology Initiative. Many large corporations have also gone into nanotechnology research because they've recognized nano's ability to help them make superior products. For example, semiconductor manufacturer Intel Corporation makes semiconductor chips comprised of billions of transistors with nanoscale features. At the time this video was created, Intel's newly released Alder Lake processors use transistors with feature lengths as low as 10 nanometers. Sports equipment companies have been using nanoparticles in tennis racket frames, golf clubs, and bike frames, just to name a few things. These examples showcase the practical applications of nanotechnology in our everyday lives. But what's so special about the nanoscale anyways? Well, working at the nanoscale allows us to unlock new properties and features of matter that we couldn't achieve at normal length scales. First of all, nanoscale structures have a far greater surface area than their larger scale counterparts for the same amount of material. Surface area is important because the surface is where a structure interacts with its environment. Therefore, a greater surface area means a greater amount of that material comes into contact with the environment, which affects the reactivity of your final product. Let's use an example to illustrate. Let's take a cube of any material with dimensions of 1 centimeter on each side. Each face of the cube has a surface area of 1 centimeter squared. Because the cube has 6 faces total, its total surface area is 6 centimeters squared. Now, let's chop that big cube into a collection of smaller cubes measuring 1 millimeter on each side. The total surface area of all the smaller cubes together is 60 centimeters squared. Now, let's do this once more, this time splitting up our original cube into a collection of nanoscale cubes measuring 1 nanometer on each side. The total surface area of all the nanoscale cubes together is 60 million centimeters squared. That's 10 million times more surface area than our original cube with the same amount of mass. We can see that we can greatly increase the reactivity of a material by making nanoscale structures out of them. This principle was used to make better catalytic converters in cars. Catalytic converters are devices incorporated into the exhaust of all cars today. They use chemical reactions to change the harmful substances in a car's exhaust gases into something less harmful. They essentially clean the exhaust and reduce air pollution. However, they can be expensive to make because of the precious metals needed for them to work. By creating nanoscale structures with the same materials, we greatly increase the surface area and thus the reactivity. Modern catalytic converters that use nanoscale materials can achieve the same reductions in air pollution while using fewer precious metals. Another reason why nanotechnology holds so much promise is that quantum effects begin to play a role at the nanoscale. This makes material properties like melting point and fluorescence size dependent on the scale. For example, let's delve deeper into how the 10th century Europeans colored glass using gold nanoparticles. The gold we see in our everyday lives is yellow. However, when you take that same material and make nanoparticles out of it, you can tune its fluorescence. That's a fancy way of saying you can change its color. When electrons absorb high energy light, they will jump into a higher energy state before relaxing into a lower energy state. Relaxation causes a photon or a particle of light to be emitted in the process. The wavelength of the photon, which determines the color of emitted light, is proportional to the energy gap between the higher and lower state, and the color of fluorescence can be tuned in gold nanoparticles by modulating the energy gap between electron transitions. 10th century Europeans took advantage of these quantum effects to create prettier architecture, but there are far more practical applications. Gold is a relatively inert element, which means it doesn't react with much. That means it's pretty safe to use in the human body. Now, combine that with the fact that gold nanoparticles have tunable optical properties and are small enough to fit into every crevice of your body. Researchers today can get gold nanoparticles to selectively accumulate in cancer tumors where their optical properties can help with more precise imaging. Furthermore, once at the tumors, gold nanoparticles can be made to emit a large amount of heat by shining near-infrared light on them, destroying the surrounding tumor cells. Near-infrared light can penetrate the skin and is benign in small amounts. Medical researchers have already shown proof of concept in the lab, but only time will tell if this technology will be commercialized. Another quantum effect that emerges at the nanoscale is quantum tunneling. This phenomenon has no classical counterpart, meaning it doesn't happen in our everyday life, so it can be counterintuitive at first. But let's try to explain by using a classical analogy. Imagine you're trying to roll a rock over a hill. Unless you push it hard enough, the rock will not roll over the hill. That is, you need to give it enough kinetic energy to overcome the potential energy barrier of the hill. However, at the nanoscale, the rules operate differently because particles are subject to the laws of quantum mechanics. Even if the rock doesn't have enough energy to go over the hill from the initial push, there is a small but finite probability it will appear on the other side of the hill. This phenomenon is called quantum tunneling. The probability that the object tunnels through the barrier depends on things like the energy of the particle, the height of the barrier, and the width of the barrier. So I know this sounds crazy, and some of you are wondering if this actually even happens. The answer is a resounding yes. Although scientists are still discovering fundamental aspects of quantum tunneling today, we've known about the phenomenon for about a century now. We understand it so well at this point that we've engineered electronic devices that operate using quantum tunneling. We'll discuss this in greater detail in a future episode about how nanotechnology is revolutionizing the electronics industry, so please tune into that when it's available. Another reason why the nanoscale is important is biology occurs at that scale. This fact underpins the medical applications of nanotechnology, also known as nanomedicine. For example, DNA is about 2 nanometers in diameter. Most proteins are on the order of 10 nanometers, and a typical virus is about 100 nanometers wide. Drawing on the natural nanoscale of biology, researchers have designed new tools, treatments, and therapies over the decades. They've also updated existing methods to make them more precise and personalized. Nanomedicine is a booming field of research with some products already commercially available. Okay, so what about the tiny robots, sometimes referred to as microbots or nanobots, roaming through your body and fighting disease at the cellular level? Although they aren't available yet, there are teams of scientists and engineers working to make these robots a reality. We'll deep dive into the science behind these robots, as well as other medical applications of nanotechnology in a future episode on nanomedicine, so please check it out when it's available. So how long before we have medical nanobots? Well, Ray Kurzweil is the Director of Engineering at Google. He's also a futurist with a good track record of making accurate technological predictions. Kurzweil says nanobots will be flowing through our bodies as early as the 2030s. He predicts they'll be helping our immune system to fight disease, making up for its flaws. Our immune system does a pretty good job for the most part, but it isn't perfect. Sometimes our immune system attacks benign things, like in the case of allergies and autoimmune diseases. And sometimes our immune system overlooks malevolent cells, as in the case of cancer. If these technologies become proliferated, Kurzweil predicts it will greatly increase our life expectancies. Nanotechnology can enrich our lives in ways once thought unimaginable. However, will we work to reap its full potential? Thanks for watching, Earthlings. In my next video, we'll discuss how researchers create and study nanomaterials and nanostructures. Thanks, and see y'all next time.